will next see the standard algorithm for computing the dominator tree in some steps. Okay, so it was completed in 1979 by Robert Arya. He is the main creator, and Thomas Lengauer, his PhD student at Stanford University. And Thomas Lengauer, he's the brother of Christian Lengauer, whose group in Passau in Bayern has developed many high-order transformations, and they have been implemented both in GCC and Clang. Okay, so the basis for the Lengauer-Tarjan algorithm is depth first search. We will not go through the proofs why this works, but we will make it intuitive. The proofs are in the book, but it will take too much time to go through them. Okay, first, a semi-dominator. It's usually identical to the immediate dominator, but not always. But it's much easier to compute the semi-dominator. So the algorithm starts with a depth first search, and then it computes the semi-dominator of each vertex. And then it will compute, it will check if the semi-dominator is identical to the immediate dominator. If it's not, then it will remember how to find the immediate dominator. It cannot find it at that point, but it will find it later. Okay. So, what is the semi-dominator? The semi-dominator is, well, first of all, I should say the following, that when we name a vertex, we use either, I mean, in general, a name such as U or V, but we let U be the depth first search number. So we write U is less than V, which means U has a smaller depth first search number than V. Okay, and the semi-dominator is a vertex, is the smallest vertex with a path in the following sense, with the following rule. So the semi-dominator is V0 and vertex W is VK. And all these nodes on the path between V0 and VK should have a depth first search number which is higher than VK. Okay, and there can be several nodes which could be, so to speak, candidates for being the semi-dominator, but it is, since it's defined as the smallest vertex which fulfills this criteria, then therefore the semi-dominator is unique. So let's look at an example. 5. It has the semi-dominator 2. Okay, first of all, there are 2 vertices which satisfy the rule that every node between the semi-dominator candidate and the and the node have a depth first search number which is higher than the node, and that is 4 and 5. For 4, there is no node, so it's between. I mean, there is no node with depth first search number less than 5 between 4 and 5. So 4 is a valid candidate for being the semi-dominator. Quite often, the predecessor is the semi-dominator, but absolutely not always. I mean, if we have branches, it's not. Okay, 2, why is that also a candidate? Because there is a path with vertices that have a higher depth of search number than 5 on this path. Okay, so 2 is another candidate. So why not 3? Okay, we take the path from 3 to 5, but this path violates the rule because 4 is in that path and 4 is less than 5, so it's not a valid path. All nodes between the semi-dominator candidate and the vertex which we start with should have a depth of search number which is higher than the node. So what we can do is to start with, what we do is to evaluate each predecessor and search backwards and follow nodes which have a higher depth of search number than the one we started with. Actually, we follow parents in the depth of search tree. When we do the depth of search, the one which creates, the node which visits a new node for the first time is the parent of that new node. So for instance, 6 is the parent of 7, 4 is the parent of 5, etc. So what we do is to check, we start a search from each predecessor of a node and follow this search. Then we follow the parent links. Actually, we use not the variable called parent, but a variable called ancestor, but it has the same value. So let's say parent for the moment. We follow the parent in the depth of search tree as long as we have a depth of search number which is higher than where we started. And then we simply select the one which has the lowest number. The parent of that. So 2 is the parent of 6. So we stop there. 2 is the semi-dominator of 5. So let's now assume that we know how to compute the semi-dominators. And what can we do? Not what we can do, but why should it not be the immediate dominator? So we can look at 5 and 2 again. I just say that I have sketched how to find the semi-dominator, but let's assume that we know exactly how to find it. And the semi-dominator of 5 is 2. And why is it not the immediate dominator? What can we do to observe that 2 is not the immediate dominator of 5? Well, we can search parents in the depth of search tree from 5 up to the semi-dominator, which must be an ancestor in the depth of search tree. And if we find a node with a semi-dominator which is lower than the semi-dominator we are looking for, that means there is an edge such as this one which goes in before we come to the semi-dominator. And therefore 2 cannot be the immediate dominator of 5. Actually 2 does not dominate 5. So the whole idea is of this algorithm is to find the semi-dominators, the semi-dominator of each vertex, and then check by searching parts of the depth of search tree to find an edge such as this one. How can we find an edge like this one? Well, it is a node with a lower semi-dominator. I mean, depth of search number of its semi-dominator is lower than, in our case, 2. Then there is a similar path into this node, which makes it impossible for 2 to be the semi-dominator of 5. Sorry, to be the immediate dominator of 5. So that is the basic idea with this algorithm.